In the previous video, we've looked at the contributions to the probe size on the sample. We will now go to the complete opposite side of the electron microscope, namely the source. Of course, in order to get a beam of electrons and be able to focus this beam to a very small spot on the sample, we first need to be able to get a free electron in space. So in this image you see a schematic depiction of the different types of electron sources that we have. In general, the electron source is fed by a high current of electrons. You see that indicated here with the blue arrows. The actual source is indicated here in white, the structure below the orange bars. At the bottom of this structure, electrons are extracted. And the electrons are extracted by a high voltage applied on this tip. And you can see the structure in gray surrounding this, which is an additional field that suppresses the emission of electrons to the side of the probe. So it helps to direct the electrons into a beam into the electron microscope column. Now there's different variants of the source that we can attach to this high current feed. First, we can have a tungsten filament from which electrons are extracted, which, as we can see if we compare this to the other structures depicted to the right, it gives us a very large surface from which the electrons are extracted, so we can reason already a bit that this can give quite a high virtual source size. We can also use a so-called lab 6 material, which is particularly used if we want to exploit photoemission in the process. I will talk about that in a second. And an important other type of source size is the field emission gun, which you see depicted to the right. The field emission gun is a very sharp tip, so sharp that actually the virtual source size is very small, but also so sharp that it enhances the electric field around the tip, similarly to what we have in a lighting rod. I will also talk about that in a second. So when we have this source and we apply a field on this source, of course we have to be able to extract electrons. So on the slide here you see a schematic depiction of a semiconductor material. So in a semiconductor material we have electrons contained in energy levels which we call the valence band, in which they are immobile. You see the valence band in this structure denoted in pink. So higher up in the valence band there's the conduction band, which is again a continuum of states in which the electrons can reside, but which is typically at very low temperatures unoccupied. Now at room temperature or at elevated temperature, due to kinetic excitation, thermal excitation, some of the electrons will cross the gap between the valence band and the conduction band and be free to move in the conduction band. So this gives us an average occupation level, which is what we call the Fermi level, which you see depicted with a dashed line in this image. Now, in order to be able to extract electrons from the material, we have to supply these electrons an energy which is typically the distance from the Fermi level to the top of the conduction band, which is what we call the vacuum level. This is the energy that the electrons need to be freed from the material. This distance we call the work function. So we have to supply the electrons inside the source material a sufficient amount of energy to cross the work function and still have a little bit of kinetic energy to travel in the space outside the material. Now how can we supply this energy? There's different ways. First of all, we can apply a very strong field. So in effect we pull out the electrons from the material. We can enhance this field even if we apply a sharp tip, as I illustrated on the previous image for the field emission gun. And so the sharp tip means the field is very strongly confined around this tip, meaning a high localization of electric field lines, so a high electric field strength locally, which helps to pull out the electrons. We can also increase the temperature of the source, which is typically what we do by the high current feed. So we raise the temperature of the tip, maybe to energies of 2000 Kelvin, such that a larger fraction of electrons is populating the conduction band and the Fermi level is shifted up so that the work function effectively is lowered. In addition, we can also stimulate the source with a laser beam and in this way get to photoemission. So the electrons absorb some of the photons, which gives them an excess energy which is sufficient to leave the material. In practice, all these effects may be used in an electron microscope. But by far the most common type of source for high brightness applications, and we will talk about brightness later in this lecture, is the Schottky source. So the Schottky source is a sharp tip, not as sharp as a field emission gun, but it's also, in addition, heated. So you see that depicted here. Completely to the left you see the electron microscope. You see the source depicted in the upper part of the column, where we see the arrow with vacuum level 10 minus 9 millibar. So the vacuum level at the size of the source is very high, so very low pressures. And this is because we don't want to have contamination on the tip, as this would ruin our extraction process. Further down in the electron microscopy column, the vacuum level is typically lower. We would have 10 minus 5 in the chamber on the position of the sample itself. Now the next image, you see actually the Schottky tip with the high current feed. So you see a typical current of about 2 amperes is brought towards the tip. This heats it up. You see here the tip glowing. And in a Schottky tip, the typical energy at which it's operated is 1800 kelvins. Now you see a further zoom in to the tip part from which emission takes place. You can see that there is a zirconium oxide reservoir which forms a small layer around the tip material in order to enhance the emission. It reduces the work function of the intrinsic tungsten material. And in the completely right image, you actually see the facet. And note that this is a very small facet, and you can also see the crystalline top, the single crystalline top from which the emission actually takes place. So the small size of the tips helps to reduce the virtual source size. Now we have seen the different probe size contributions for the probe on the sample in the previous video. Now let's look at which of these probe size contributions are actually affected by the choice of our source. These are 2. Of course, it's the size of the virtual source size, which forms a major limitation, but also the chromatic aberrations, the relative energy spread, can be affected by the choice of our source. And so we've seen that the Schottky source or other heated sources are brought to a very high energy. This also means that there is a larger difference in energies between the different electrons, so a larger energy spread. Of course, if we would have a cold tip, a cold field emitter, the energy spread would be much more reduced, but we could extract maybe less electrons from the material, or we would have additional ways, except for heating, to extract the electrons. So now we know how we extract electrons from the material and get a current down our column. So it's important to realize that the electron microscopy column for the rest consists of vacuum. We don't want the electrons to scatter once they have left the material. So all the environment is vacuum up till we reach the point where the electrons hit the sample. Now here you see a schematic depiction of electron microscopy column. Now we see the source depicted in green on top. We see a beam also depicted with the green rays going down to the sample, which is depicted in blue. We see schematic depiction of different types of lenses. We will talk about lenses in a later video. And of course now there's a current going from the source to the sample. The free beam of electrons constitutes a current, so a number of electrons per second, or a number of Coulomb units per second, which goes down and hits the sample. Now we also see in this image that there are several apertures in the system. This is typical for electron microscope. We also know this from optical microscopy. But apertures in electron microscope are important. They are important because they limit the opening angle of the beam, and we have seen that we want to limit the opening angle of the beam as this affects spherical and chromatic aberration. Of course, the use of these apertures also affects the amount of electrons passing through this aperture. So when we extract a certain current from the source, if we would measure the current just below the source, this may be different from the current that we measure later on in the beam current, because the beam has passed an aperture. Of course, ultimately, we have a specific current on the sample after passing multiple apertures, and this is what we call the probe current. Now, these currents do not need to be the same. Nevertheless, it is important to get a high amount of current on the sample, as every electron that we have on the sample generates signal, a backscattered electron or one or multiple secondary electrons. So the more current the more electrons we have on the sample, the more signal we generate, the sooner we can step to the next pixel and the faster we can image. So if this current is not conserved throughout the electron microscope column, what other quantity can we use to characterize the performance of our beam? Now this quantity is the brightness, or better, the reduced brightness. We can get an intuitive feeling about the concept of brightness by looking at typical light sources as we know. Of course, first we have a light bulb, which you see in the image here. We know a light bulb typically consumes a few watt, and this few watt of light is emitted in all different directions. On the other extreme we have a laser, and we know a laser gives a very intense beam, but we also know that a laser maybe consumes a few milliwatt, so much less power than the light bulb. Still, in the laser, all this light intensity, this few milliwatt, is directed into a single beam at a single spot. Now this is what we call a high brightness. All the power is directed into a specific direction, while for a low brightness beam, the direction, so the angles under which the beam travels, is much larger. So brightness, by formal definition, is given by the equation depicted here. So we look at a small fraction of area and a small fraction of solid angle in which a small fraction of current is emitted, which is why we have the subscript d here for all the quantities. So now the brightness is given by the amount of current dI passing to an infinitely small area dA into a solid angle d omega. So this incorporates the opening angles into the equation. And we also, in this case, scale by the voltage at which the beam, the electrons, have been accelerated. If we do not scale with the voltage, we refer to the brightness. If we scale to the voltage, we refer to the reduced brightness. The important thing here is that reduced brightness is a conserved quantity throughout the electron beam trajectory. So it's not affected by apertures. Apertures limit the current, but this current limitation is equivalent to the opening area of the beam. So we see as dI scales with dA in the brightness equation that this is incorporated for. Similarly for the opening angles of the beam, as d omega is in the equation. And by changing the voltage at which the electrons are accelerated, we change the angles at which the beam travel. So by scaling with the voltage, we also include this effect. Now I don't want you to understand this concept of brightness into great detail, but I want you to know that it's a conserved quantity, and I want you to know that you have an intuitive feeling for what brightness means. Now, with the concept of brightness and the fact that this is a conserved quantity, we can look at the relation between the probe size and the current in the beam on the sample. So first we recap from lecture 3, where we talked about scattering, the definition of the solid angle. That is what you see depicted on this slide here. Now this solid angle can be approximated as pi times alpha squared. And next we see in the image on the bottom left, again the image of the virtual source size. In this derivation we denote the virtual source size, the diameter, with dV. So at the virtual source size plane we have an opening angle of the beam alpha. Okay. Now at the source we can get the equation for the reduced brightness by plugging in the parameters: the current I, the size of the emission area, the virtual source size, which is pi dV over 2 squared. We incorporate the solid angle, pi alpha squared, and the voltage at which the electrons will be accelerated, V. This is the reduced brightness at the source. We know this reduced brightness at the source is the same as the reduced brightness that we have in the probe on the sample. Now if we look at the sample plane, which factors have changed? Of course the current now is not conserved, so we denote this as IP for probe current. Next we have the size, the area that the beam travels through on the sample, which is pi times the virtual source size times the transversal magnification squared. Next we have, if we assume the opening angle of the beam to be the same, a term pi alpha squared. And we have the voltage at which the beam travels, which we can denote with V in this case. Now we can equate these two equations. The equation for the reduced brightness at the source plane to the reduced brightness in the probe. And from this extract a value for the probe size diameter. So the factor mt times d that we have in the equation for the reduced brightness at the probe size. And we can get the equation that we see here at the bottom of the slide. Now, it may be good to redo this equation for yourself, but I don't want you to know this derivation by heart or be able to do this at the exam. So we see from this derivation that the final probe diameter, the contribution from the virtual source size demagnification to the probe size, is dependent on the square root of the current. So we see that we cannot limitless increase the current in the beam. This will go at the expense of the virtual source size magnified probe size contribution. And we also see a dependence on 1 over the opening angle of the beam. So note now that for all the factors that we have for the probe size contribution, the opening angle of the beam comes in different relations to the opening angle. So now, if we would have certain operating conditions of our microscope, for instance, a certain reduced brightness, which is a source property. You see that depicted here in the caption of this figure, a reduced brightness of 10 to the power 8, which is a typical factor for a high brightness source. If we assume a certain virtual source size, in this case 50 nanometer, we assume a certain operating voltage of our beam, the voltage with which the electrons hit the sample. We assume a certain energy spread, a spherical aberration coefficient and a chromatic aberration coefficient for the electron microscope itself. Then we can indicate all these different contributions to the probe size in one figure. And this is what is depicted in the figure you see here. So on the horizontal axis you see the opening angle. Note that the opening angle is in milliradians. We know that milliradians is the typical magnitude of the opening angle in an electron microscope. And the vertical axis you see the final probe size contribution in nanometers. Now you see different lines drawn here. First, the blue line gives the contribution given by spherical aberration. Note that the plot is logarithmic and the curve here gives a third power dependence. In purple we see the chromatic aberration coefficient, which goes as the power 1, indeed a slower slope than the spherical aberration curve. Next we see in red the contribution of diffraction to the probe size. Note that the contribution of diffraction decreases with opening angle, as we expect from the 1 over alpha dependence, and it was actually what we exploit in light microscopy. We go to larger opening angles to get a tighter focused beam. Then also we see the virtual source size dependence on opening angle for different currents in the beam. So you see here two different cases, one for when the current is 10 minus 18 times the reduced brightness, and one curve for when the current in the beam is 10 minus 16 times the reduced brightness. We see that with a higher current, the contribution of the virtual probe size to the probe size on the sample is larger. Now, of course, for each opening angle, we can indicate the dominant contribution, and we can indicate the sum of all these contributions to the total probe size, which is what you see indicated by the hyperbolic-like curve here. So we see that for very small opening angles, the virtual source size demagnification dominates, while for higher opening angles is very quickly the spherical aberration coefficient that dominates. Of course, we should also realize that this is for a very small 0.5 electron volt energy spread. So if we have more energy spread, the chromatic aberration coefficient may become dominant, because this is also dependent on delta E over E0. So I want you to be able to understand how these different probe size contributions relate to opening angle and to current, which is the main message of this video.